Namaskar students, let us start the next lecture, which is electrostatics. You are already familiar with these concepts, but I'll take you one level deeper into this subject. And first, we'll discuss electrostatic field and potential. What is our motive? Our motive would be to learn to use of Coulombs law and both integral and differential form of Gauss's laws for continuous charge distributions. That should be our focus. And we'll do electrostatics, of course. Electrostatics, Coulombs law, Gauss's law. We'll figure out divergence and curl of E, which will lead to potential formulation of electrostatics, that is field as gradient, Poisson equation, Laplace equation. In electrostatics, there are the job is, of course, it is charges which are fixed, and so there will be charges which we'll call as charge density or rho, from which you can calculate the electric field, or from given the electric field you should be able to calculate charges, and in potential formulation you should be able to do from charge to produce the potential, to figure out the potential, or given the potential find out the charge, or connect these two. So basically the electrostatics has the job to be able to connect the charge density with electric field and the potential. My advice at this stage would be go through all the examples in your textbook very carefully. In fact, this is an advice which I will give for all the chapters. I will do some examples which will be in addition to the examples given in the book. Full vector treatment in problems is important. You are more familiar with taking symmetry argument and using or calculating things in a scalar treatment. We would insist on full vector treatment all throughout while you are solving the problems. Then, of course, one of our main aims is to connect the maths with physics to sharpen our intuition, and of course discuss physical implications of each problem. Let me start with a thumbnail history of electrostatics. I'll give such thumbnail histories in magnetostatics and electrodynamics later. Can you read what is written on the top of this slide? This is written in Greek. I hope you know enough Greek letters to be able to read this. What is written here is electron. Now, electron in Greek means amber. Amber is actually a tree raisin. And this is the first material which seemed to have given a feeling of electric phenomena even as early as in Greek culture. So Thales of Miletus in 600 BC describes this. 1,000 years later, William Gilbert sort of made this discipline of electrostatics a scientific one by writing a book called The Magnetar. He was in Cambridge, and he's the first one to have used the term electrics for these insulators who gave charges under friction. And then Stephen Gray, another scientist or physicist, who figured out the role of the conductors, that actually conductors can't be charged by rubbing. Okay, and he investigated the role of conductors. He was not in favor of, in the good book of Isaac Newton, and because of that, he suffered a lot and remained a pauper till till Newton died. And after Newton died, his contributions to electrostatics was recognized by the Royal Society and was given Copley Prizes twice. And then around 1750s, Benjamin Franklin, who's considered the founding father of United States, a diplomat, printer, inventor, postmaster, and all sorts of abilities, he experimented with electricity and came up with these two fluids, okay, that is both positive and negative. What he eventually called positive and negative got reversed later, but this two fluid theory of electricity, and they used to store them in what the jars called Leyden jars. In fact, in physics, many things were fluids. Heat was a fluid called caloric. Electricity was a fluid. Ether was a fluid. So this was the time when intellectually everything was a fluid. But Franklin also made the connection between the fire of the sky, that is lightning, the charges produced in the cloud are the same as that one obtains by rubbing cocks. And he, in fact, invented the lightning rod. He was also responsible for the conservation of charge, principle of conservation of charge. Joseph Priestley, chemist, mainly a chemist, and he already anticipated that the force law for charges would be an inverse square law. This is same Joseph Priestley who brought about the chemical revolution by discovering oxygen. John Robson, in around 1769, already started measuring the inverse square law and came up with 2.06. And Henry Cavendish set up elaborate experiments which to this day you can actually do in an undergraduate laboratory to prove the inverse square law. But the credit of discovering the law and finally finalizing goes to Coulomb, and that was published in 1785, which you know as Coulombs Law, which is the basis of all static electricity. And then Friedrich Gauss gave in 1835 the Gauss's law, actually published in 1867, but he had formulated it by 1835. Gauss's law should be also true for any inverse square law force, that is for gravitation. And Newton did prove it in his Principia. In fact, he knew the theorem but could not prove it. It took almost 20 years to be convinced of his proof and gave finally an extremely beautiful proof. But in connection with electrostatics is Gauss who had first formulated that, and that's why it goes by the name Gauss's law. And Maxwell, of course, whose equations we study, he redid the experiments of Cavendish, and from 2.06 or Cavendish 2.8 10 to the power minus 3 error bar on inverse square law brought it to almost 10 to the power minus 5. So with this brief thumbnail history of electrostatics, let's get into the subject proper. We know charges are intrinsic property, and there are three things which we all know, that charges come in pairs, there's the principle of conservation, and they're quantized. Let's go over some of the salient features. Come in pairs, yes, plus, minus, or neutral. But does it mean that it's either electron or proton? It's just that it has to be in plus and minus. Or is it matter and antimatter, that is electron and positron? Well, that's a mystery that in our universe is dominated by matter and not antimatter. We can figure them, we can produce a positron, but it gets quickly annihilated. So it's matter. We don't, we have a hydrogen atom, but we do not have a positron moving around an antiproton. Okay, so as matter. So it's just that it comes in pairs. Who made electron negative? That's of course the force of history. We could have as well made electron positive and proton negative. Negative, yes. Okay, but the fact that charges come in pairs, okay, which is distinct from in gravitation, where mass comes only in one variety. Okay, though both obey the inverse square law. The principle of conservation of charge is extremely important. What it says is that if I have an isolated system in which there are plus charges and let's say minus charges, then the total charge, that is pluses and minus both, okay, the sum of the two charges must be maintained unless of course there is a flow of charge from outside. Okay, so within this there will be many processes might be going through, but you cannot produce an extra charge by only internal processes. Okay, let's give examples that we already know. In a charge balance in chemical reaction, on the left side of the chemical reaction must have the same charge as the right side of the chemical reaction, or even a nuclear reaction, or even electron pair production. Okay, if a photon gives rise to a pair of electron and positron. In fact, this principle was first stated by Benjamin Franklin, and he writes, "It is now discovered and demonstrated, both here in the United States and in Europe, that the electrical fire is a real element, or species of matter, not created by friction, but collected only." This was in 1747. And we all know charges are quantized. In fact, we have assigned a value which we know to the 10 to 12 decimal places, 10 to the power minus 19 Coulomb. And we know, and hence charge is quantized. But they come in such large numbers, 10 to the power 20, 10 to the power 23, that they can be considered continuous, just as we consider continuum mechanics, in which mass is considered, though we know as continuous, though we know that it is made up of discrete atoms and molecules. Is there evidence of quantization? Plenty now. Okay, almost every day in the laboratory there are phenomena in which underlies the phenomena is that quantization of charges. Okay, we'll talk about some of them later. But we know that the particles called hadrons, like proton, is also composed of quarks, and proton, for example, has charges which is plus 3e, plus 2 3e, and minus 1 3e. Okay, there is quarks, except that these quarks are not free. We cannot separately get them out of the proton because of the strong nuclear force, and hence by quantization we really mean electronic quantization, not really the quark quantization, though they are also quantized. In solids there have been phenomena in which the electron behaves as if its charge is a fraction, like 2/3 and 1/3 and so on and so forth. One does not really mean that the electron gets fractionated, but the phenomena cannot be explained without invoking fractions of electronic charge. And for such phenomena, they have earned Nobel Prizes, okay, and they're extremely important even from practical point of view. But that's a story for another time. Let's come to Coulomb's law basics. Okay, this is the basis of electrostatics. What it does, it codifies all experimental observation. So we know that if there is one charge, Q1, and there is another Q2, then the force on 2 due to 1 is in direction, okay, which is connecting the two, like R12. So this is R12, okay, this is Q1, this is Q2. And the distance is R12, and hence this is R12 square. So that's the force, and of course this also experiences the force. But this is all about static charges. First thing is, this is electrostatics. The statement is about static charges alone. The separation distance is uniquely definable, which assumes some sort of point charges. Okay? Otherwise, if there's an extension, then you won't know where to take the distance from. The direction is along the separation vector, of course, and it's important to note that this law tells us that the interaction is really pairwise. If there was a third charge, okay, then this will also interact with the two, but that this charge, the new charge, will not interfere in the way Q1 and Q2 interact. And so it does not interfere in their mutual interaction. This is one of the bases for superposition being valid in electrostatics. And also remember that the force is directly proportional to the charge of one of them, not square of it or any other function. And that linearity, that it is a linear function of the charge, okay, and the fact that interaction is pairwise, it is the basis of superposition. What does the epsilon naught do? It is the same function as g in gravitation that gives the strength of the scale, okay, and that's a constant, and we all know it, okay. I will not, but it fixes the constant. And of course, we know since they come in pairs, they'll attract or repel, the like charges repel, unlike ones attract. And they obey inverse square law. So I have sort of restated in words what is written as a part of Coulomb's law. And it is compatible with Newton's third law. In fact, let's look at Coulomb's law in terms of its range and validity. It is valid over an astounding scale in terms of distance. We know it is valid till 1 Fermi. This is nuclear distances. The size of nuclear is of the order of 1 Fermi. Inside the nucleus, of course, it is nuclear forces, strong nuclear forces take over, so we do not know whether electrostatics is valid below 1 Fermi, and to astronomical distances, 10 to the power 6 to 10 to the power 9 kilometers, it has been proven almost experimentally. It's compatible with special theory of relativity. In fact, Einstein's search for special theory of relativity started with electric phenomena or electrodynamics, and it is completely in tune with special theory of relativity. And this has now been adapted to work with the broader integration with magnetism, so electromagnetism. It can be adapted to electrodynamics, knowing the limits of static or the velocity under which even the static conditions can be worked. And while doing quantum physics, we did not have to change our electrostatic Coulomb's law. So it works with quantum physics. So it's universal. It gives rise to universal phenomena from atoms, molecules, ruling the world of chemistry, the biology, to astronomy. Almost every aspect of the universe that we inhabit. And how strong it is 10 to the power 42 times stronger than gravity if you take two electrons. Okay, and uh, and yet, in astronomical scale, gravity still rules. We had discussed this in the first class back in the introduction. The crucial aspect of Coulomb's law is that it is an inverse square law. And people have been worried, is it really proportional to 1 by r squared? Or is it that this epsilon is only a small quantity and we can't measure? Is it exactly 2 as an integer? Or is there a quantity which is plus minus epsilon because of our experimental errors? This has deep implications for almost every aspect of the physical world that physicists study. And hence, there has been a lot of effort to measure this error, possible deviation from inverse square law epsilon. Cavendish, of course, measured 3 into 10 to the minus 2. Maxwell almost did his same experiment and to improve it to 5 into 10 to the minus 5 100 years later. And now, see, and all these are different in different years and different methods. And in 2002, the last experiment brings it epsilon to the limit of less than 10 to the power minus 20. And even beyond that, there are currently propositions to even bring this lower. There are new experiments proposed which will bring the range of epsilon to less, if at all. There's reasons to believe it would be exact 2, but physics or science doesn't take it from that kind of belief. It has to be measured. And this measurement has implication on what is the possible mass of the photon. We consider photon to be massless, okay? But depending on this epsilon, we can say that how close, what could be the maximum mass of a photon if photon has ever mass. How is that connected? Because photon is the carrier of the, in terms of particles, the interaction is carried by the photon. So if it is 10 to the minus 20, then it is that the mass of the photon is less than or equal to 1.2 10 to the minus 45 grams. Okay, or its associated inverse Crompton length is 4.3 10 to the minus 14. Okay, if you do not know this, don't worry, but these two are related. And so if even slightest of mass of photon is detected by experiment, that would change our conception of the physical world in many, many ways. Okay, so though I'll not discuss this any further, you can refer to this paper which was in 2004. And here the precision that epsilon, the error bar, is plotted over from 10 to the power 0 to 10 to the power minus 20, okay, over years. So 1775, okay, around this 1773, Cavendish, to around 2002, 10 to the power minus 20, all these determinations have been plotted to visually see how this is an astounding Y scale, 10 to the minus 20 to 20 orders of magnitude. That is, after point there are 20 zeros. Okay, and the significance of that. So that's the kind of experiment that one can do. As a part of introduction, this is enough. Let me now get back to my notebook.